Okay, so here is a worked example for a probability functions question. This one basically is a continuous function, but it's based on a quadratic function. A continuous random variable x has the probability density function. And you see it's different between 0 and 2, which is kx squared, and there's this quadratic function between 2 and 4, 0 otherwise. We don't know what k is at this point, and that's in fact the first thing that we've got to show. Now I've sort of done my best to sketch this using a tool, and it basically looks like this. No significance in the two different colors, except of course it's I've put the shape together with two different curves, and outside the range 0 to 4 it's just 0, so it's just flat there. So that's what it looks like. Now this involves integration, because we've got to find the area under a non-linear graph, a curve. So this actually involves integration. So if you haven't done integration, then this will obviously be a bit more of a challenge to you. But I suggest you kind of hang in there, because actually it's not the integration you need is not so complicated, and you may be able to pick up something from it which will help you with other similar problems before you actually cover integration proper. So let's go back to the question. Right, so we've got this function. It looks like this. I mean, I've actually drawn this knowing what the value of k is, but so it is really just there to illustrate what we're talking about. Show that k equals 3/16. So now this is a probability function. So the area underneath is equal to 1. And in order to form an equation, basically we know that this curve is x squared here, and this is kx squared, and this is kx squared minus 1.5x plus 3. So if we want the total area under this curve, then we have to integrate it in two parts, 0 to 2 and 2 to 4. And of course, when we're integrating, what we're doing effectively is summing all these infinitesimally narrow bits, which have a width of, well, let's say delta x, denoted effectively by this dx here, and a height of kx squared. So that's what the integration process actually does, and we're doing that between 0 and 2. And then between 2 and 4, we're doing this other function. And of course, the sum total of these has got to equal 1. So that's the point. So if we just do our integration on this, then the k is a constant, so that sort of comes outside. X squared, we apply the power rule, so we add 1 to the index, that makes x cubed, divide by the new index, so that's x cubed over 3. So what we're trying to do now is evaluate between 2 and 0 this function kx cubed over 3. And if we apply the power function to the power rule to this, then our kx squared again becomes kx cubed over 3. 1.5x, so that's x to the power of 1, so we add 1 onto that, that's x to the power of 2x squared. And then divide by 2, we get minus 1.5x squared over 2. 3, well, 3 is 3 times x to the power of 0, isn't it? So x to the power of 0, add 1, that's x to the power of 1, divided by 1 is divided by 1. So that would become 3x. We're evaluating that between 2 and 0, and that between 4 and 2. So what this means is that we're going to evaluate this expression at 2, the value x equals 2, and then subtract its evaluation at x equals 0. And that's what that is. So that's going to come to 8 over 3 k minus, well, it's obviously 0, isn't it? As soon as we stick a 0 in there. So that is this. And then we're going to do the same thing here. So this is the evaluation of that function there at 4. And this is its evaluation at x equals 2. So, and all that equals 1. Now, I've not done the working out here. Try and keep it concise and on one page. But basically, we've got an equation in k there, so it really just needs a bit of algebra to work that through. Be a little bit careful with signs and denominators. But if you work that through, that will indeed give you k equals 3/16, which is what we were asked to show. Right, second part of the question is find the probability that the random variable is between 1.5 and 3. So in terms of the graph, the 1.5 will be here, 3 will be here. So it will be the area under the curve between 1.5 and 3. So again, we're finding the area. It's a proportion of the total of 1, isn't it? So total probability under the curve represents certainty. The random variable is bound to fall between 0 and 4, but we just want a portion of it. So for finding area, we're doing the same thing. We're finding the area under the curve, which is the integral between, well, of course, we're going to do it in 2 bits. So we've got to do 1.5 to 2, which is this function, and 2 to 3, which is this. So in terms of the integral, then this is it. We're integrating kx squared. I mean, we know k is 3/16, but I've just left it like that for the moment. Kx squared between 1.5 and 2. And we're integrating kx squared minus 1.5x plus 3 between 2 and 3. So we're going to apply the power rule to those as we did before, and then evaluate between those limits as we did before, and that's going to give us a value of 0.727 to 3 decimal places. So the area there looks about right, doesn't it? As a sort of sanity check. Okay, so that's the second part, and then show that the upper quartile of x is 2.41, correct to 2 decimal places. Well, if it is 2.41, which would be about here, this would mean that the area underneath from 2.41 up to 4, actually up to infinity, but it goes to 0 after 4. So let's just confine ourselves to 4. From 2.41 up to 4, that area would be a quarter. Given that the total area underneath the whole thing is 1, this would be a quarter of it. And that's what we mean by this 2.41 being the upper quartile. So again, a very abbreviated form. In order to work out that area, we are going to integrate the function. Well, we're not interested in this this bit. It all comes under the red bit, which is kx squared minus 1.5x plus 3. And we're going to integrate that between 2.41 and 4. And that will give us the area of that right-hand tail. Well, I've not sort of develop this right through, but we just follow the same process in doing that, and we come to an answer which is actually very close to 0.25. So indeed that area is 0.25 above 2.41, and therefore that gives us to conclude that the upper quartile of x is 2.41, correct to 2 decimal places. Okay, so that is that. So I've cut down and cut out all the calculations just to keep it concise and simple. But hopefully that has been useful and interesting. And thank you for listening.